Welcome to BaseBoostDepth, exploiting larger baselines for self-supervised monocular depth estimation. Monocular depth estimation aims to estimate the per pixel depth for a given input image, and in this case is trained without the need of ground truth data. From multi-view stereo, we know that wider baselines generally lead to a decrease in depth error, as shown. Building on this foundation, we leverage wider baselines for monocular depth estimation to achieve state-of-the-art results. In previous methods, like MonoDepth 2, during training, source images from narrow baselines were used to reconstruct the target frame. This involved using a depth network to estimate the per pixel depth of the target image, followed by a pose network to estimate the ego motion between the target and source images. With these estimations, we can reconstruct the target image using an inverse warping function, which requires the source image, depth of the target image, and the pose from the target to the source image. We then compare our reconstruction of the target image to the true target image using photometric loss. By applying minimum aggregation, we identify the best reconstruction on a per pixel basis, forming our main loss function. Additionally, we create reconstructions of the target image from the adjacent stereo image. Rather than using narrow baselines, we could use larger frames of separation or wider baselines to create reconstructions of the target image, resulting in an updated set of source images. However, this approach has little effect on the final results due to the use of minimum aggregation. Here, a bar chart shows the percentage representation of each source image in the final loss for a single iteration. Since narrow baselines are easier to reconstruct, they dominate the final photometric loss representation. We could address this by solely training with wider baselines, but this presents its own challenges. Standard image-based metrics suffer from poor performance, as can be seen in the highlighted row. However, we observe substantial improvements in edge-based accuracy metrics. The accompanying video demonstrates significant edge detail improvements, but overall poor performance in depth. Our objective is to achieve these or better edge-based details while surpassing image-based performance compared to our benchmark MonoDepth 2. To achieve this, we introduce a curriculum learning-inspired optimization strategy, which gradually transitions from smaller to wider monocular baselines during training. This scheme is divided into a warm-up and boosting stage. In the warm-up phase, we limit our baseline width to 2 frames of separation, and after 10 epochs, we drastically increase the baseline width, forcing the network to learn with wider baselines. Using wider monocular baselines leads to 2 major problems: underestimated pose and temporal artifacts between frames. Let's address the underestimated pose. The graph shows that as we increase the source frame separation, the error in estimating the pose between the target image and the source image increases substantially. To counter this, we use incremental pose estimation, breaking down the pose estimations into smaller increments within a larger interval. This results in a much better pose estimation with large baselines, as demonstrated. Next, we address temporal artifacts between frames. Wider baselines exacerbate the effect of dynamic objects, occlusion, and brightness inconsistencies on our reconstructions. To solve this issue, we introduce triminimization, which minimizes the errors by reconstructing the target image in the center frame from triplets of future and past frames. When performing incremental pose estimation, we found that correcting the pose only for the smallest baseline for the optimization process was most beneficial. Incremental pose estimation was not used for the other reconstructions. Inspired by this, we introduce error-induced reconstructions. By incorporating an error into the translation of the pose, we generate error-induced reconstructions, which we apply to our minimization process. Combining all of these contributions, we achieve state-of-the-art results for image-based metrics and edge-based metrics. Furthermore, when using the pre-trained depth network instead of performing the warm-up stage, and solely using our boosting stage, we outperform the benchmark MonoDepth 2. Formally, we achieve state-of-the-art performance on the Kitty dataset. Further testing on the SYNS dataset shows that state-of-the-art results for image-based, edge-based, and point cloud-based metrics. Here we present some qualitative results that illustrate the impressive performance of BaseBoostDepth compared with our benchmark MonoDepth 2. We observe fine details such as mesh railings and fences being illuminated, and leaves being pronounced. In summary, BaseBoostDepth introduces curriculum learning-inspired optimization strategy, incremental pose estimation, triminimization, and error-induced reconstructions. Thank you for watching. Be sure to check out the paper.